So, good evening. Should I do something here? So good evening. Tomorrow my talk will be outdated. Indeed, I want to talk to you this evening about the latest Nobel laureates of the Physics Nobel Prize, namely the 2020 Nobel Prize. And as you probably know, the Nobel Foundation will announce tomorrow the 2021 Nobel laureates in physics, which means that today was really my last opportunity. And I would like to thank the organizers for this very timely rescheduling of my lecture. So, who are the Nobel laureates of the 2020 Physics Prize? These three people: Roger Penrose, Reinhard Genzel, and Atelier Ghez. And why did they get, what did they get the Nobel Prize for? Well, this is a citation from the Nobel Foundation. They got the Nobel, so it was awarded in, was divided, one half awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half jointly to Reinhard Genzel and Atelier Ghez for the discovery of a supermassive compact object at the center of our galaxy. So I would like to explain what that sentence means, and to do that I will try to answer 5 questions. In fact, the first 2 really concern the Nobel Prize. So why did Genzel, Ghez and Penrose get the 2020 Nobel Prize in Physics? And that's related. How can one observe a black hole if it is black? And then I will, if I have time, deal with more speculative questions, which are not the reasons for the Nobel Prize of 2020, but nevertheless are quite interesting. What is Hawking radiation from a black hole? What is inside a black hole? And is there a connection between black holes and wormholes, or what are wormholes? So this is a long program, and in order to answer these questions, there is a question number 0 that I have to address, which is to give you some knowledge of the general ideas behind Einstein's theory of gravity, also known as general relativity. So the general relativity of the citation from the Nobel Foundation. So I will be rather sketchy. I will try to convey the main ideas and the general principles, but of course without being technical. Now there is one key thing that will be used to understand black hole that comes already from the special relativity that Einstein developed in 1905, which is that the speed of light, so the speed with which light propagates, is a speed that you cannot overcome. So that's the maximum speed. It's a huge speed, so in practice it's not a limitation, but that's a speed that you cannot, that's a limiting speed. Now, when I say it's invariant, it means that all observers will agree that that speed is given by that value, and that's a limiting speed. So let's talk about the Einstein's revolution that introduced in 1915, when he developed the theory of gravity compatible with the general principles of relativity. So that's general relativity. Well, it's a revolution because instead of describing the gravitational interaction in terms of a force, like Newton did, he described the gravity in terms of deformation of space and time. So in technical term, a deformation is called a curvature. So it describes gravity as the curvature, the bending of space and time. So space and time are not anymore a fixed framework in which physics take place, but instead it's space and time are subject to physical laws. And since we cannot think of space independently of time, the two go together, one really talks about space-time in a word. I will illustrate that later. And so the space-time will be deformed and will not be given by an Euclidean space-time, but will be deformed, will be curved, and the amount of curvature will be the bigger the gravity is. And this is really a revolution because, as I said, previously gravity was described in terms of a force, as we have learned in high school, but here it's really a fusion of geometry and physics, which is described, contained in general relativity. Now, but what does this mean? So I will try to give that a little bit more intuitive for the non-expert. So what do we mean by space-time is curved, space-time is deformed? Well, I will take an example from 2 dimensions. So imagine a 2-dimensional flat surface. That's the top picture. So you have regular squares. So that would be undeformed 2-dimensional space. And then if there is gravity, if you introduce a mass, of course, here it's it's an analogy, yeah? But like all analogies, it has its virtues. It illustrates the fact that the 2-dimensional geometry will be deformed and will be deformed most near the gravitating body. But space-time is 4-dimensional and there is a time, so it's not exactly like that, but that gives you an idea. The idea is that something which is flat, regular, all the squares are equal, become deformed, and you can see that the squares which were originally equal are not anymore equal close to the source of gravity. So this is what we mean by space-time becomes curved. And the bigger the masses, so the bigger the source of gravity, the gravitational sources, the bigger the deformation of the space-time geometry. So this is illustrated again. It's an illustration with all its limitations, but it gives you the correct idea that light gravitational sources will deform less space-time than heavier ones, like the yellow one is, or green one is deforming space-time much more in its vicinity than the red one. Okay, now because of the deformation of the geometry, the behavior of the analog of straight lines will be different. So in Einstein theory, objects follow straight lines, but because space-time is curved, straight lines will not behave as in undeformed Euclidean geometry that we are being told in high schools. So to show an example, zero curvature means the undeformed space, the 2-dimensional plane, and we see that 2 animals which are walking parallel to each other, they start parallel, they remain parallel at equal distance. But if we are on a 2-dimensional surface which has curvature, which is deformed with respect to the plane, well, parallel lines will meet or will diverge. And this behavior explains the behavior of objects in subject to gravity. Now, we cannot think of space independently of time, so there is really space-time, so time is also curved. What does it mean that time is curved? Well, it means that gravity slows down time, so that the pace at which clocks will tick will depend on where you are in a gravitational field. So if gravity is stronger, the clock will tick slower than in a place where gravity is weaker. So to take the example of the Earth, the strength of the pull of the Earth on you is weaker if you are at the surface than if you are at a high altitude. And because of that, the clocks will not tick in the same way. Time is deformed, time is curved, is bent. Now, of course, the effect is extremely minute in the case of the gravitational field of the Earth. So it's 1 second per 10 to the 6 years, 3 million years, but the effect exists and has been tested. I will come back to that later. So the geometry of space is deformed, the geometry of time is deformed in that sense. And as I said, this accounts for all gravitational phenomena. For instance, the motion of planets can be understood in the Einstein's view as the sun deforms the geometry around it, and because of that, the planets which follow what they think are straight lines, well, will follow lines that actually come back to the original position. They will follow closed line. Actually, not exactly. There is a slight deviation of Einstein theory with respect to Newton theory. In Newton theory, there would be ellipses. In Einstein theory, the ellipses will slowly move. There will be an advance of the perihelion, and this has been observed. But this can be completely understood not in terms of forces, as in Newton theory, but in terms of the deformation of the geometry of space-time around the sun, in the vicinity of the sun. Now, light will also be subject to that. Everything lives in space-time, so light will also be affected by the deformation of the geometry, and that will translate itself, for instance, in this following effect, that so if you look at the true position of the star, the light ray that it emits and that we receive on Earth is bent by the gravitational field of the sun. And so if we extrapolate in a straight line, we think that the star is at the apparent position which is drawn on the picture, but in reality, it is at the true position drawn on the picture. And you can tell that this effect exists because if the sun would not be in the way, well, then you would see the apparent position of the star would coincide with the true position of the star. But when the sun is between the star and the Earth, the true position does not coincide with the apparent position. It's again a very small effect, 1.75 seconds of an arc, but that's twice as big as the effect predicted by Newton's theory. So, and that has been observed already in 1919. Of course, you can ask the question, if the sun is in the way, the light from the sun will completely hide the light that we could receive from the stars. So this is an experiment that you can make when there is an eclipse. And that was done in 1919. So this is an effect that has been measured, and I will come back, well, actually I will develop this effect a little bit now, because that's an important effect that is being used by astrophysicists to understand better the universe, and in particular to measure masses. So let me illustrate more spectacular deviation of light effects. So you can imagine that if the geometry is, well, the source is sufficiently far and the deflector is sufficiently big, actually you can see two images or more than two images of the same object. So this is, the mechanism is drawn on that picture. We are on Earth. We observe a quasar which is behind a galaxy. The quasar is sending light, so it's a quasi-stellar object which is pouring a huge amount of energy, in particular in the form of visible light, and so the light can come to us following two different ways because there is this galaxy that is deforming the geometry around it. And so we would see then two different images of the same quasar, which is behind the deflector. And so this is illustrated in that picture, but there are real pictures which are even more spectacular, what has been called the Einstein cross. In the Einstein cross, you can think that you can see 5 objects, but there are really only 2. There is a deflector which is in the center, and behind the deflector there is an object that you see 4 times. And you see it 4 times because the light that it emits is deviated by the deflector which is at the center. And actually there is an interesting history about this observation, that originally astronomers, astrophysicists thought that they were really seeing 4 different objects, but then they realized that when something happened to one of them, let's say a brighter spot somewhere, exactly the same thing happened to the other 3. The same bright spot would appear. And that would be in contradiction with relativity that tells us that signals cannot propagate faster than light. That was instantaneous. So it was like a well organized ballet. And then they realized that actually it was the same object that they were seeing 4 times, and there was then no mystery of the fact that you would see a repetition of the same changes. Now, so there are many examples of gravitational lenses, and they are actually extremely useful to measure masses that I will report later. So this is another image, again, a central deflector and 3 images. Now you can imagine, and that actually was already conceived by Einstein, that if the geometry is such that the deflector, the lens galaxy, and the distant object are perfectly aligned and the galaxy is spherically symmetric, then you will not see 1 image nor 2 images, but you will really see a ring of images, because all the signals sent in all directions will reach you, and you will see this so-called Einstein ring. And this has been observed. So this is an example. Well, of course, it's not perfectly aligned and it's not perfect spherical symmetry, so the image is brighter at some places, but you can see that there is a ring of images that has been formed. So the deflection of light and this effect predicted by Einstein theory is a real, true effect that has been observed. Now, concerning the curvature of time, actually we are all every day checking, verifying this prediction of Einstein theory when we use GPS, and GPS is in all possible applications now, because the GPS has to take into account the fact that time clocks do not tick at the same rate in different places in a gravitational field. So the principle of the GPS, I will be rather quick here, because it's not the main purpose of my lecture, but the principle of the GPS is that you have a constellation of satellites, the position of which is known with great accuracy, and these satellites are sending signals with information on when the signal was sent, and we know the position of the satellite, so by triangulation we can determine where we are on Earth. But for that to work, the clocks on the satellite has to be perfectly synchronized with your clock that you are using on Earth, because you compute the distance from the satellite by measuring the time it takes for light to propagate from the satellite to you. And so if the clocks are not synchronized, you will get a wrong measure. But since the clocks on the satellite are not ticking at the same pace as a clock on Earth, the small effect that I mentioned, well, we have to take into account that effect if we want to have a precise, an accurate GPS measurement of the position. And this is done by offsetting slightly the frequency of the clocks on the satellite. And as I said, this is a phenomenon now which is verifying every day. It was, when predicted by Einstein, it was thought as a bit bizarre, but now we are, this bending of time, this curvature of time is something that is, I would say, in everyday life. Okay, so these are the characteristics. I will skip that. Now, I should stress that gravity is a very weak force if we compare gravity with the other force, between quotation mark, this Newton description. But if you compare it with the pull exerted by electromagnetic, if we compare that with electromagnetic forces, well, we know very well that a very small magnet is as strong as the Earth to keep a needle fixed to the magnet. So that means that the gravitational attraction of the Earth is weaker than the attraction of a small magnet on a needle. So it's in usual situation, gravity is very weak, and the deformation of space and time is rather small. To give another idea, if you compare the ratio of the electric force to the gravitational force between an electron and a proton, well, it's huge, as you can see. And so in order to have some significant deformation of the geometry, you need big masses and compact objects. So I gave you here some ideas of the order of magnitude. These deformations are small for the Earth and for the Sun, but they they get much more sensible for neutron stars, which are stars which have the mass of the order of the Sun, but compacted in a sphere of radius 10 kilometers. So it's a compact object, and at the surface of a neutron star, you would have a deformation of the geometry, which is more like 10 to the minus 1, or black holes. So I need to tell you now a little bit more about black holes. Now, black holes are remarkable predictions of Einstein theory, extremely fascinating object. What are they? So they are compact objects, the gravitational pull of which is so strong that in order to escape from the gravitational pull of the black hole, you would have to go faster than light. But since we cannot go faster than light, nothing escapes from a black hole, not even light, which is the fastest thing that you can imagine. And hence, they have been given the name black. And they are extremely fascinating, not only from the point of view of astrophysics, as I will describe, but also they raise important questions theoretically. Now, I will have to use some slightly technical terminology. A black hole is really characterized by what we call an event horizon. I will make that more concrete in a second, which is a boundary in space-time, which is a one-way surface. So if you are within the horizon, so this is a boundary that surrounds the black hole, that defines the black hole, and if you are inside, you cannot go out. But if you are outside, you can go in, you can fall into the black hole. So it's a one-way surface to the black hole. And you can so only be crossed inwards towards the center, not outwards. And let me give an analogy, which again, like own analogy, has its limitation, but I think it conveys very well some important features of black hole. And here is the analogy. So imagine a boat on a river. So this is the river, but there are falls. And as you know, the stream of the water, well, very far from the fall, it can be very quiet, still water. But as you approach the fall, the speed of the water, the stream, will be bigger and bigger and bigger. Okay. Now we have a boat, and the fisherman on the boat can only go at some maximum speed. I mean, he cannot row arbitrarily fast. So he has a maximum speed, and as long as he's on that side of that line, where the speed of the stream is smaller, so speed of the river, velocity of the river, is smaller than the maximum velocity of the boat, he can go this way and he can go that way. But if he crosses that point of no return, if he goes that way, the stream is faster than its maximum speed. So even if he wants to go upstream as fast as he can, he will go down to the fall. So this line is the analog of the event horizon of a black hole. Now, in the case of a black hole, so well, I already used the term, well, it's already the terminology of the black hole here, but think of this as water in a sink, in a kitchen sink, and there is a hole, and you open the hole, and again, very far from the hole, water is rather still, but if you go close to the hole, the speed of the water is greater, and this is just to show that the event horizon, instead of being a line, in the case of black holes, is a closed, one dimension is missing, so here it's a circle. In general, in the case of a black hole in space, it will be a sphere. But so there is again this one-way surface. You see, the velocity here you can escape, because there is a stream going this way, but not sufficiently fast to prevent you from going in that direction. But once you are here, the speed is so high that even if you try as much as you can to go this way, you will be attracted down the hole. And the case of the black hole is, in a sense, a hole in the geometry of space-time. So a black hole deforms so much the geometry of space-time that the same phenomenon occur, but it's the pull of gravity which plays the role of the river stream. And so you have exactly the same phenomenon. And the pull of gravity far from the hole is weak. And so you can go this way out from the black hole or to the black hole, well, this is always possible. But then once you have crossed the event horizon, this limiting one-way surface, you can only go inwards. It's impossible. You would have to go faster than light because the pull of gravity attracts you to the center too strong. You would have to go faster than light to go in the opposite direction, and that's not possible. Which means that since nothing can go cross the event horizon from inside to outside, no information can be sent from inside the black hole through the event horizon. And an outside observer would have no knowledge of what happens inside the black hole. So if he can send a friend to go to the black hole, but the friend will have no way to communicate with him once he has crossed the event horizon. Now, in the case of the black hole, it's, as I said, it's a sphere. I mean, we have a central singularity surrounded by a sphere, and don't cross the sphere. Now, what are the orders of magnitude? Well, in the case of the sun, so if we would have a black hole which has the mass of the sun, well, it would be a sphere with a rather small radius, 3 kilometers. A black hole with the mass of the Earth would have this 1 centimeter size. So you can see that it's indeed extremely compact. Now, another feature which is interesting about black holes, which I will illustrate first in this analogy, is that imagine that the man on the boat, the fisherman, has a friend very far, and he communicates with the friend. He sends small boats, for instance, which have this maximum boat velocity upstream. And the small boat has some information. Well, I have seen this. I have fished so many fishes. Every 5 minutes, he sends a boat with telling what he's doing. Now, as he approaches this horizon, this point of no return, since the stream is getting faster, it's clear that the time it will take for the boats, small boats with information, to give information, to transmit the information to the distant observer, will take, the time will become greater and greater and greater. And when he crosses the point of no return, actually he can send a small boat with a maximum velocity upstream, but that small boat will remain on the point of no return because the two velocities will be opposite and equal. So he will not be able to communicate. So you could see there is an increasing delay in the information that you can send as you are falling into the black hole. And the last small boat that you send when you cross the horizon will take an infinite time to reach a distant observer. But for the fisherman, I mean, going downstream, it takes a finite time to reach the horizon. So you can see this phenomenon of time dilation, that the time depends on the state of motion, on where you are. Time is, as I said, is something which is deformed. And nothing special will occur to him when he crosses this point of no return. I mean, if there is no rocks and nothing, if the stream is equal and uniform, well, nothing special will be felt when he crosses the point of no return. Of course, something will happen later, and I will come back to that later also, but for the moment, he does not realize that something is going to happen to him. And the same is true in the case of black holes. So if you have a fixed outside observer which receives information from a falling object, the processes get slower and slower and slower, and clocks will appear to tick more slowly than those further away from the black hole, just like on the boat. And so the falling objects appear to slow as it approaches the event horizon. It will take, from the point of view of the outside observer, an infinite time to reach the horizon. But at the same time, because the signals are spaced, more and more spaced, they will get weaker, dimmer, redder in terms of frequency, and so it will disappear. The object will fade away, and actually that takes a finite time. But for the observer falling into a black hole, nothing special occurs. Time goes as it should go, and it takes a finite time to reach the event horizon where nothing special happens for the point of view of the falling observer. It's of course later that bad things will happen, but this I will discuss unavoidably so, because you cannot go back. Okay, so now I can talk about the Nobel Prize. And I think I have only 12 hours to speak about the 2020 Nobel Prize. So it was divided in two, and one half was given to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half to Reinhard Genzel and Ghez for essentially observing a black hole at the center of our galaxy. So let me explain first the work of Penrose. Actually, the work of Penrose played historically an extremely important role, because initially physicists did not believe the solution of Einstein theory describing black holes. So actually Schwarzschild, I think 2 years after Einstein formulated his theory, discovered a solution which describes black hole. But it's only later that physicists understood the physical significance of the solution, and there was a lot of resistance in the physics community, because they thought that the solution was pathological, and in realistic condition the black holes would not form. I mean, this bizarre behavior, there would be some kind of principle forbidding the bizarre behavior that I described, although I tried to describe it to you in a way that did not sound too bizarre. But at that time things were not so clear, and even Einstein himself did not believe that this was a sensible physical solution, the solution describing black holes. And it's much more recently, so I told you the black hole solution was found in 1917, it's only gradually and in a sense much more recently that the idea that black holes are physical objects that have to be taken seriously emerged. So that view changed through the work of Oppenheimer first, that showed that, well, with other people, that somehow stars with a mass that was too big would collapse and form a black hole, and that was unavoidable. And then Wheeler and Hawking and Penrose also established results that such that the black holes became gradually accepted by physicists. And in particular, Penrose provided a very convincing, and I think I would say the definite convincing step. He demonstrated using highly original mathematical techniques that if you believe in Einstein's theory of gravity, and we have every reason to believe in Einstein's theory of gravity, then the formation of black holes is unavoidable. If you start with physically reasonable initial conditions, black holes will form. And that's why he was awarded half of the Nobel Prize last year. And actually we have learned more about black holes since the 60s. There are really 3 different types of black holes. Stellar mass black holes that are formed by gravitational collapse of star at the end of the evolutions if they are too massive. We have supermassive black holes at the center of galaxies. I will mention one later. And you have also so-called primordial black holes, much smaller black holes that might have been formed soon after the Big Bang with much smaller masses. But only the first 2 have been observed. Okay, so I explained the reason why Penrose got the Nobel Prize. Why did the other 2 why did they get the Nobel Prize? And for that, I have to address the question, how does one observe a black hole? So Penrose got the prize for theoretical work, mathematical predictions. Genzel and Ghez got the prize for observations. So I have to tell you, how do we observe a black hole, and how is it even possible to observe a black hole if a black hole is black? Does not send light to you. So how do you observe a black hole? Well, you observe a black hole indirectly through the very strong gravitational pull on matter and light in the vicinity, as I will try to illustrate. And actually there is a very good precedent, which is the discovery of Neptune. So it's the same type of idea. So Neptune is one planet, and it was first found by mathematical prediction by Le Verrier and not by empirical observation. So here is Le Verrier. And how did he predict the existence of Neptune? Well, there was a planet that had been seen visible, Uranus, but its behavior, its orbit around the Sun, didn't quite fit the predictions of Newton's theory. There were irregularities. Now, you could have said, well, that's because Newton's theory is incorrect, but Leverrier said, no, perhaps these irregularities are due to the fact that there is some other gravitational source nearby, and maybe we can explain the irregularities. And he did the mathematical computation, and he postulated the presence of another planet, and he could see that all the irregularities of the planet Uranus could be explained if there was indeed that other planet, Neptune. And then he told observers, well, please look at this place. At that time, you will see something, and that was indeed observed with a telescope in 1846. But so he was able, in a sense, to see Neptune without seeing it in the sense of receiving light from it. And there is a very nice sentence from Arago, which I will show here. We said, Monsieur Leverrier a aperçu le nouvel astre sans avoir besoin de jeter un seul regard vers le ciel, il l'a vu au bout de sa plume. Bon. He had also information about the planet Uranus, but which were, of course, quite important. But indeed, to see Neptune, that was a prediction. Another example is what we call dark matter. You probably heard about dark matter. So the matter that we see, so-called visible matter, is only a small fraction of the matter in the universe. There is another component of the energy, which is called dark matter. Now, dark matter, by definition, is dark, is black, you don't see it. So how do we know that there is dark matter? Well, we know there is dark matter through its gravitational effects. And one popular way to measure the mass of dark matter, to see that there is dark matter, is to use the gravitational length effects that I described. So here we have, well, the picture is rather explicit. There is a galaxy. We are there on Earth in the Milky Way, looking at the galaxy. We see this effect of gravitational length, and one can show that the mass, of course, the bending of light will depend on the mass. The more it's bent, the more massive it is. Now we can measure the bending, and then we can infer the mass. We can compare what we infer from the bending of light to what we see, and we can conclude that we see much less than what is really there in the middle. And that's how we can say that there is dark matter. I mean, there are other ways to get dark matter, and they all converge to the same picture, but that's one way to measure dark matter. So again, we can see dark matter without seeing it by this effect. So what are the observable effects that can enable us to detect the presence of a black hole? Well, for instance, through the orbits of stars near a supermassive black hole at the center of galaxies, that's one way, which I will describe. I will describe all three. We can also observe a black hole indirectly through the violent effects that exist just outside the event horizon, and also through gravitational waves as it has been done more recently. So let me explain how the proper motions of stars around orbiting a black hole can tell us about the black hole. Again, it's an idea which should be familiar to some of us, at least if we remember our teaching at high school. How do we know the mass of the sun? Well, of course, no one goes with a scale to put the sun on a scale and look at the reading and say, well, this is the mass of the sun. So we have an indirect way to know the mass of the sun, goes back to Kepler. By observing the motion of planets, one can weigh the sun because, and that's a precise law that follows from Kepler and Newton, the period, if you know the period of revolution of a planet and its distance from the sun, you can determine the mass of the sun responsible for the motion of the planet. Now, I wrote the formula that goes back to high schools. If you forgot it, never mind. I mean, the idea is that by measuring the period of revolution, which is something you can do, for instance, the Earth has a period of revolution of 1 year around the sun. By measuring the distance from the sun, which is slightly more difficult, but you can do also, then you determine the mass through that formula. You don't need to remember the formula, but maybe you can remember that If the sun were 4 times as massive, so you multiply m by 4, you would have to turn twice as fast around the sun to stay at the same distance. So indeed, that gives information about the mass. And so what the 2 Nobel laureates did, they observed the motion of stars around the center of the galaxy. So there is, at the center of our galaxy, the Milky Way, a supermassive object, which is called Sagittarius A star, around which the stars of our galaxies are orbiting. And so by looking at the orbits, we can determine the mass of the supermassive object at the center. And by measuring all exquisitely parameters of these motions, we get a lot of information about Sagittarius A. Now, it's a difficult thing to do because you would like to observe stars which are close to the galactic center in order to get accurate measurements. And also, if they are not close to the galactic center, there will be all sorts of other gravitational perturbation by the other stars. So you want to have something which is close to the galactic center, also in order for that object to have a period that you can measure with accuracy. For instance, the sun, which is far from the galactic center, has a period of 240 million years. You don't want to wait that to measure precisely the period. You want a star which has a period of a few years around the galactic center, and it has to be close to the galactic center. So it's extremely difficult because close to the galactic center there is a lot of molecular clouds, there is a lot of dust, so you have to extract a very signal from a lot of garbage, if I can say so. And this is what these people did. Genzel and Ghez were able to measure with extreme accuracy the motions of planets close to the galactic center and conclude from the parameters of these motions that at the center of the galactic center we had a gigantic black hole. So they were able to measure the mass just as we weigh the sun. Well, they did it for the black hole at the center of the galaxy, 4 million solar masses, and they have an idea of the region of space which is occupied, and it's sufficiently compact to be a black hole. So we now fully understand that sentence. It's for this work that Genzel and Ghez got the Nobel Prize last year. Now there are other ways to observe a black hole, which I would like to mention because it's always good to see that we have complementary evidence for the same thing. And after all, a black hole being difficult to observe by definition, it's good to see that there are independent ways to come to the same conclusion. Now this is a different thing. This is, and actually that was a picture in the news not so long ago. So, and it's based on a different effect. So a black hole can grow by absorbing gas. So a black hole is not just in empty space. I mean, there is an environment. It might be another planet, another star, a companion star. There is gas, dust. But of course, a black hole has a strong gravitational pull. So it eats everything which is nearby. And so matter, a lot of matter will fall into the black hole continuously due to the huge gravitational pull. And this matter in general has some angular momentum, so before plunging, actually the falling matter will form what we call a rotating accretion disk just outside the event horizon, so before plunging through the horizon. And this is a very crowded space. So particles will, when they spiral into the black hole, there are many other particles doing the same. The black hole is attracting everything. And so there will be a lot of collisions. And all these collisions will release a huge amount of energy, will heat the system. And because of this heating, that's a huge amount of electromagnetic radiation, for instance, will be produced. X-rays will be produced also. And that is just before plunging through the horizon. So there is this accretion disk outside the event horizon. And so this light that is formed there can reach us, and we can see it. And so this is an artist's image, but then I will show a real image. So you can see at the center, very well, you can see the black hole. Well, it's slightly darker here. And then there is this accretion disk. As you get closer, it's warmer and warmer. The temperature is higher and higher, so that's why it's brighter. And the matter is just falling, spiraling into the black hole. And these are, as I said, extremely violent phenomena with a large luminosity. I mean, the black hole has such a terrible gravitational pull that there is a huge conversion of gravitational potential energy into other forms of energy that we can see. And there was a program, the Event Horizon Telescope, which is really many observatories which have observed a potential black hole. I will tell you which one in a second. Actually, they observed the center of the galaxy, but they don't have yet images. But they also observed the center of another galaxy. And so there are many observatories coordinating their observation, and they were able to observe directly the immediate environment of the event horizon of that black hole, the supermassive black hole at the center of the galaxy Messier 87. That's a galaxy nearby, well, nearby at cosmological scales. And here is the image that they produce. So this is a real image. So this is the accretion disk. So you see that there is this black region, but then around there is some accretion disk. And there are brighter zones and less bright zone, but this is due to the Doppler effect. So you can tell, and actually that's not completely obvious, but there is something that I should say also, and that's the bending of light. In fact, the disk, the accretion disk is in our plane, so it's edge-on. But because of the deflection of light, we think it's just in the perpendicular plane. But so there is light brighter, that's due to the Doppler because it's coming towards us, it's the Doppler effect. But so this is really a huge black hole, 6 billion solar masses, and one can show that it eats, so every 10 years, the equivalent of one full sun. So it's really, you can see the proportions. Now, another way to observe black holes, a third way, which has been made available much more recently, and these are more like stellar mass black holes. They can merge. Black holes, well, there are other black holes in the universe, and black holes can collide. They can merge, either with other black holes or with stars, and to form, so if there are two black holes, they merge and they form a single black hole. But this phenomenon releases a huge amount of energy, partly in the form of gravitational waves. And this is something that you can see. So again, the gravitational waves will propagate in space, and we will receive some gravitational waves from that event, and we can just measure the characteristic of the gravitational wave. So what are gravitational waves? They are disturbances in the geometry of space-time that propagate with the speed of light. They are extremely difficult to detect because gravity, as I told you, is a very weak coupling. Furthermore, these objects, these sources are very far away. So it's really a remarkable experimental prowess. But people have been able to detect gravitational waves from the merging of black holes. So it's a different way to see black holes, not through visible light, but through the gravitational waves that they produce in these events. So this is one of the detector, LIGO, probably you heard about it. It's a very difficult experiment, observation, and so this is based on interferometry. I will not describe the experiment, but just to show that it has a big scale, since it has two 4-kilometer long arms, and you make light interfere, and the effect of the gravitational waves will slightly change the length of the arms, and this is what you detect. Okay, and they announced, so this is relatively recent, they announced the event in 2015, and if I had been asked to give the same talk, let's say a few years ago, since they got the Nobel Prize for that, I would have talked more about that experiment. So the conclusion of all these different types of observation is that black holes are everywhere. And they can be of different types, either quasars, I mean huge in the center of galaxies. So quasars are quasi-stellar objects, so this is these powerful engines at the center of galaxies, or they can be in more like a few solar masses, can be 70 solar masses, but not a million. Okay, so these are more like stellar mass black holes. Okay. So, well, this is really what I wanted to say about the Nobel laureates and about their work. Now I will address topics, and much more quickly, I'm afraid, which have not yet been awarded a prize by the Nobel Foundation, which are much more speculative. And you know that the Nobel Foundation is very cautious in giving the Nobel Prizes. So these are more conceptual questions related to black holes, but important questions, because if we understand these questions, we will be able to understand another important problem in theoretical physics, which is to reconcile gravity, Einstein's theory of gravity, and quantum mechanics. As I said, I will be more qualitative here. I will address just very impressionistically these topics, but I just want to show and to convey the idea that this is an active field of research. I mean, there are still many things that we want to understand about black holes, not just from the observational point of view, but also conceptually. So Hawking radiation. So in a remarkable piece of work, Hawking predicted that black holes were actually not completely black. If you take into account the effects of quantum mechanics, they will emit thermal radiation, black body radiation, physicists call it, which is a rather robust prediction of the theory, and this is called Hawking radiation since it is Hawking who predicted it. So it's some sort of tunneling effects, and through that tunneling effect you have some radiation which is emitted by black holes, so they are not completely black. But you can show that this temperature that they have is extremely small, actually inversely proportional to the mass of the black hole. So stellar mass black holes, or the huge black hole at the center of our galaxy, have a very, very, very small temperature, much smaller than the temperature of the universe. So they would actually attract mass rather than radiate. But small black holes with a very small mass will be hot and will evaporate actually through Hawking radiation. Now, Bekenstein and Hawking also showed that not only do black holes have a temperature, but they have also an entropy. Now, what is an entropy? Well, it's clear that I cannot explain in 30 seconds what an entropy is, so either you know or you don't know. So I will only again be very impressionistic about what entropy is, but let me, well, maybe you are sensitive to the poetry of the words, okay? So entropy is a measure of the disorder. So it actually counts the number of macroscopic configurations of the system that would lead to the same macroscopic properties. So if I look, for instance, at the air in this volume here, it has some density, some temperature, but we know that it's composed of a lot of molecules, and actually many configurations of these molecules will give the same temperature and the same pressure and the same density, and so many microscopic configurations would lead to the same macroscopic properties, and entropy is related to that. But if black holes has an entropy, and if we want to have the statistical mechanical interpretation of entropy, you ask the question, what is it counting? I just told you entropy counts the number of microscopic configurations compatible with given macroscopic parameters. And, well, no one knows, really, because in order to do that, we need a good microscopic description of gravity, so a consistent description of gravity at the microscopic level, and no one has really has achieved that for the black holes that we know. So string theory, which is a very promising way to quantize gravity, has given partial answers, and very promising answers, but the full answer to the question is not yet known. So I'm afraid maybe this I will skip, because I think I am behind time, no? 2 minutes. Okay. Well, it would be like infinite compression. Now, maybe I want to... Well, a related question is a loss of information, but maybe I don't explain that. If you have questions, you can ask me after the lecture. I would like to go to the more interesting topic of what happens to someone who falls inside a black hole. So, what the Einstein equations predict is that there is a gravitational singularity at the center of black holes. Now, what does that mean, gravitational singularity? It means that the forces, the tidal forces of gravity, I mean the pull and the stress of gravity are infinite. That's why we call it a singularity. Which means that if you are falling into, well, Schwarzschild means it's a type of black hole which is spherically symmetric. I don't know why. So if you fall into a black hole, you can forget about Schwarzschild. If you fall into a black hole, you will be torn apart as you approach a singularity, and in fact even crushed to infinite density when you reach it. So clearly it's not a very pleasant thing to do, but as soon as you have, it's like here, you see, as soon as you have crossed that line, even if things are peaceful here, if there are rocks there, I mean, you will fall on the rock and that's it. Okay, now, however, in the case of a river, we can say there are rocks and the water continues on the other side. In the case of gravity, it's much more dramatic because it's a singularity in the geometry of space-time. Remember, gravity is space-time geometry. So it's a very dramatic phenomenon. It means the end of time. So what happens beyond the singularity is a question that we cannot really answer for the moment because we don't have the tool and we don't have the theory to answer that. We just know that it will be very unpleasant. We will have these infinite tidal disruptions, but how to describe it more precisely is not something that is in our power now. Now, we think that this really means that the theory of general relativity cannot be applied all the way to the singularity. A singularity is not something physical, so the theory breaks down. That somehow quantum effect, quantum mechanics, this other big revolution of the 20th century, should play an important role, but we don't have a completely consistent quantum theory of gravity yet. So that's something that we cannot answer for the moment, and there is active research on that topic. Again, string theory brings ideas. Singularities have an interesting structure, but that would be another talk again. So I would like to finish with something maybe more science fiction-like, which are wormholes. Now, what is a wormhole? So a wormhole is a structure which links different points in space-time, which can be very distant. I will illustrate that with picture on the next slide. So you can think of it as a tunnel that with two ends that separate space-time points, which provide a shortcut to go from one of these points to the other. Now, this is abstract, but wait for the picture. Now, but you have to be a bit patient. So Wikipedia tells us theoretically a wormhole might connect extremely long distances, such as 1 billion light years, or short distances, such as a few meters, or different points in time, or even different universes. Why wormhole? Well, the name is suggested by think of an apple, a worm. So that's the surface of the apple. You can move on the surface, but the worm make a shortcut. So through the wormhole, you can go from that side to that side without having to go the long way around. So that's the image that is behind wormhole. So to give you the idea, you can see that, well, I don't have a pointer, but you have two ways to go from, let's say, the upper sheet to the lower sheet. Either you go, the normal way is really the bent way, but then there is a shortcut in between. So it's just like a wormhole. So that would connect different regions of space, and this is called a wormhole. Another example of a wormhole would connect two different universes. The upper, again, I mean, we can only draw things on the plane, so we have to drop some dimensions. But you have an upper universe, a low universe, and then some tunnel that connect the two, and that's what we call a wormhole. Now, why are we interested in wormholes? Because they are consistent with Einstein's theory of gravity. it's not completely clear that macroscopic realistic wormhole can exist. So let me go quickly over that. We have solutions that describe them, but the known solutions are non-traversable in the sense that you would have to go faster than light to go through them. So these wormholes are dynamical. So if I show this wormhole here, so the wormhole will create, so you would have two disconnected universes, then they will be connected by this tunnel for some time, and then it will pinch, and they will get disconnected again. So you have to go fast to go from one universe to the other before the pinching, and one can show that the known solutions are such that you would have to go faster than light, so it's not non-traversable. But we think that maybe microscopic wormholes could play a significant role in the problem of quantum gravity, and in particular in the problem of concerning the information paradox, of which I didn't speak. Okay, so I think it's high time to get to the conclusion and maybe to have a black hole cocktail. So the conclusion is that black holes are fascinating prediction of Einstein's theory of gravity. They are very robust predictions from the theoretical point of view, but they also play a key role in astrophysics. And it's very interesting to see the history because, in a sense, black holes were already there in 1915 when Einstein had developed his theory. Well, we could have predicted black holes and all these things that I talked, but it took a very long time for the physics community and for the astrophysicists to understand the role of black hole. But now black holes are really commonplace, and there are stellar-sized black holes, gigantic black holes at the center of galaxies, and a lot of observation. But they are not only interesting astrophysically, they also raise many conceptual issues that I didn't have much time to talk about, but I really want to convey the message that this is not a finished subject. There are very many important and interesting questions, issues concerning gravity and black holes, and many people are working on these conceptual questions. So thank you very much.